Okay, so we've got the atomic solution to Schrodinger's equation programmed in here. Let's add our next case, which will be for the molecule. So I'm going to add a page to the tab control for molecule, and I'm going to add another case to our potential type case structure in the block diagram. And I'm going to duplicate the atomic case in order to do this because the molecule is very similar to the atom. These controls here look kind of weird because they're actually floating above the tab control currently, but if I just select them, move them around a bit, I can get them to snap into the page. Okay, so what are the differences between a molecule and an atom? Well, a molecule, we now have two atomic nuclei that we want to simulate, along with one electron. This is going to be one electron molecule. So the first thing is we don't need this mass anymore because we don't need to calculate a reduced mass because we can't, because reduced mass is how you calculate the relative motion, the kinetic energy for the relative motion between two bodies, and now we have three bodies. We have one nucleus, another nucleus, and the electron. So we need to use an approximation here. This is called the Born-Oppenheimer approximation. And the assumption is that the nuclei are not moving very much relative to the electron, and so they will be fixed in place. And we will only be calculating the kinetic energy for the electron. And so we are just going to use the electron mass here. This is a pretty good approximation. If you solve the atomic case using this approximation, your answer will not be that different because the reduced mass of a nucleus and an electron is very close to the mass of the nucleus anyway. So this isn't mu anymore, so I'm just going to call it m. I'm going to call this output terminal m. I'm going to call the variable m, just so it's more accurate. Second thing we can do is we can delete this effective potential term that was accounting for our centrifugal potential. Because we are no longer in a spherically symmetric environment here, that will be meaningless. So we're not going to be able to calculate bonding, pi bonds or anything like that involving p orbitals. We can just delete it. We're going to be looking at sigma bonds between s orbitals, essentially. Although we must keep in mind this is a one-dimensional calculation. Real sigma bonds have overlap in more than one dimension. So this isn't exactly that either, but it will be qualitatively very similar. And some of the trends we see will still be very useful to explore. Okay, so what do we need though? We need the charge of nucleus 1 and nucleus 2. So I'm going to call this Z1. And I'm going to call this Z2. And what is our bond length going to be? One convenient way to set this up is to make one nucleus be at 0 and the other nucleus be at whatever the X max is that we're currently plotting. That way we can avoid issues, numerical issues that arise when we have those negative infinity potentials. So I'm actually just going to take the X max control and wire that in here for a variable called big R, which will be the bond length, the distance between the two nuclei. Okay, so having that, we can complete our potential here. We need three terms in our potential. One for the interaction between the electron and the first nucleus. So let's turn this expression into that. So Z1, delete that. Negative Z1 divided by all this. What is the distance between the nucleus and the electron? Well, it's just x. And actually, we do need to shift this. So x plus 1 e to the negative 10 or so should be fine to stop it from being to having that negative infinity point. Then we need another term. So I'm going to paste that there. I'm going to just press enter and make this go to the next line so it's easier to organize. This will be the attractive interaction between the electron and the second nucleus. So we're going to use negative Z2 here. And this is going to be R, the bond length, minus X will give us that distance. Okay, let's add another term. Get rid of our extra semicolons there that I accidentally copied. What is the final term? It is the Coulombic interaction between the two nuclei. So plus Z1 times Z2. And the distance between the nuclei is just defined as that big R. So don't need these parentheses. So that should work, hopefully. Okay, so we got one. This will be H2 plus is what we're going to be simulating here. Let's see if it works. That looks good. We've got one atomic potential for one nuclei, one atomic potential for the other nuclei. The electron is equally likely to be found on either. We can change X max to change the bond distance. You can see there is still some interaction here at long bond distance because this will asymptotically approach the atomic energy, which was negative 109 something or another, inverse centimeters. This is just an electron in an s orbital in one atom or electron in an s orbital in another atom. Okay, it's basically just solving the atomic case. But as you bring the two nuclei closer together, you should see the overall energy lowering as you approach, reasonable bond distances. So somewhere around here. Now we're getting some constructive interference of our two wave functions. The overall energy is getting lower. Continues to get lower, but at some point it will have to start going up again because the nuclear repulsion takes over. And so somewhere right in there now it's going up. So what is the equilibrium bond length of this H2 plus molecule? Well, it's wherever the energy is the lowest, which seems to be right about, just looking at that number, still getting lower. Still getting lower. Oh, we're close here. Yeah, now we're going back up again. So somewhere around here. 1.3 something. Angstroms seems to be a reasonable bond length for a molecule. That will not be the experimental bond length of H2 plus, because as I said, we're only doing this in one dimension, and an actual atom in the world has 3. But the trend of what this molecular potential looks like is very much similar to what it is in real life. You can also look for excited states here, of course, by shifting. I suspect at this bond distance, the first excited state is way, way higher in energy, and it's not even below the ionization potential. So But as we go out to slightly longer bond distances, yeah, there it is. You can see it there. And there will be no minimum in that potential, because that state is the antibonding orbital. So there is no minimum in an antibonding orbital because there's no bond. The energy just keeps increasing as you make the bond length shorter. So this will just keep decreasing here as we go to longer bond lengths. Okay, one more thing to complete our program. What about our transition dipole moment? We've got that. You know, our overlap integral here for calculating the transition intensity there. For the atom, we had that Jacobian for spherical coordinates to worry about that ended up canceling out the x in our transition dipole moment. But this now, we're not doing anything to assume that there's more than this one coordinate here. This is one dimension again. So we're going to go back to using our x points here for the transition dipole moment. And so we can calculate molecular transitions. So here's the excited state here. I'll just save that as a wave function. And then I'll shift down to the ground state. This potential should be allowed. Here we go. This would be a transition from the bonding to antibonding orbital. That should be allowed because the symmetry is changing, just like the particle in a box. And you'll notice these wave functions do indeed look similar to a particle in a box. All right, well, that completes our molecular case here. So that's it for now.